In this video, we'll discuss electric potential energy. We'll compare it to gravitational potential energy, which you have experience with. This will be helpful when we need to distinguish between electric potential energy and electric potential. We know that when two charges interact, such as this large charge over here, positive Q, and this small test charge, that there's an electric force between them. Also, generally speaking, capital Q, big Q, is considered to be much, much bigger than a little test charge that we put somewhere in the vicinity of this charge. Analogous to the gravitational force on an object, due to its location relative to Earth, there's a potential energy associated with this force. This kind of potential energy is called electric potential energy, and it results from objects' charges, not their masses. The definition of electric potential energy is potential energy associated with a charge due to its location in some electric field. And this charge, little q here, is in an electric field that is being produced by this charge, big Q here. Looking at a positive charge in a uniform electric field, here's the positive charge, and this electric field is uniform because all the field lines are parallel and they're all pointing in the same direction, and they're all the same distance apart. This is a field that might be produced by two parallel plates that are oppositely charged. So let's imagine this charge moving in this uniform electric field from, say, point A to point B. There's a change in the electric potential energy associated with the charge's new position after it moved from A to B. The change in potential energy depends on the charge itself, its magnitude, and also, of course, its sign. It also depends on the field strength, the strength of the uniform electric field, and it also depends on the displacement. So if I put this displacement marker here, how far it moved, the displacement. The change in the electric potential energy can be written as this equation here. Change in electric potential energy is equal to the opposite of the charge times the field strength times the displacement. So in other words, the change in potential energy, electric potential energy, can be thought of as the charge multiplied by the electric field strength multiplied by the displacement. The negative sign in this equation reflects the fact that the potential energy will increase if Q is negative, and it will decrease if Q is positive. So in summary, for electric potential energy, the electric field does work on a positive charge. So if the charge is positive, if the charge moves along the E field, parallel with it, then the work that's done moving the charge in the direction of the E field causes the charge to lose potential energy, or causes the system to lose potential energy. This is if the charge moves along with the electric field. If it's a negative charge and it moves along with the electric field, then the system gains electric potential energy. Now, if the charge is moving opposite the electric field, as long as it's a positive charge, the system gains potential energy. And likewise, if it's a negative charge moving opposite the field, the system loses potential energy. Remember, this is because of the fact that the electric field vector points in the direction that a positive charge feels the force due to the electric field. And one last note here to sort of follow up on this summary, that as with gravitational potential energy, it's the change or the difference in that potential energy that really has any physical meaning for us. And we can choose any point as a reference point to measure this change in potential.